Here is the algorithm sketch for the merge sort. So given a list, we first divide into two halves. This is just a blind cut. Given long list, you just cut in the half. So we have a second half and first half. Then recursively sort first half and second half. Then we have two lists. Each of them are sorted, so we just combine together. Then that is a merge sort algorithm. Let me show you how this algorithm works as an example. So we have a list. First step is a partition into two lists. Suppose this is a one list and this is another list. Originally, so you had this long one list though. So you have two lists now. Then each of them, first half and second half, are sorted independently. So they are now sorted. Then how do we merge is begin with the very first element in each list. So 1 and 3. So 1 is smaller, so we pick up 1 first. Pick up 1 first place here. And then again compare the ones at the very head, at the very front. Now 3 and 5. 3 is smaller, so take this one. Construct the next element. Now, so you keep repeating, compare whatever is at the head of the list. 4 and 5, so take a 4, put there after 3, and then 5 and 8 take 5. Now 8 and 7 take 7. Now 8 only, so 8 and 9 are put together. So that's a merge algorithm, combine algorithm. That is the merge sort. Then the here is an actual example of those one. So suppose we have the data as follows. This one. So black ones are now unsorted ones, and then when you come back, the red ones are sorted ones. So first step, we partition this one into two. So left half and right half. So they are separated. And then we do recursively. So we have four data. So we divide those two into two halves there. Still we have 2, so we divide into 2. Now this one. So for each of those ones, we continue to do so. This one we divide into two halves, divide into two halves, and so on. Now we have only one data, so recursively sorting one data is trivial case. Now we build it up, return the result. So between 26 and 33, we combine together by comparing the ones at the very first head of the list, the 23, 30, 30. So they are put together. We do so in each of those ones. So those are put together. Those are put together and the like. Now between those two sorted list, we compare the first ones, 26 and 29, take 26 first, and then 30, 30, 29, take 29, 30, 30, 35, take a 33, whatever left over put together. So this is sorted out. We do the same thing for this partition. So 12 and 19, and there's nothing, so 22 only. So we just 12 and the 22, 12 comes. 19 and 22, 19 comes. 22 is left over there. So it's sorted out now. Now between those two sorted list, we do same thing. 26, 12, 12 first. 26, 19, 19 first. 26, 22, 22 first. The rest, there's nothing on the right, just the rest just put at the end. Now this is done. So that's how merge sort actually works. Then time complexity. Time complexity is that for each layer, like a binary tree, we need to put together. Put together means each data should be compared and then put together, compared and put together. So all of the data are processed once at each level. So the time complexity is how many levels do we have as we divide those data into two halves. So 2 and 2 and 2 and 2. Then this is a binary tree problem. In binary tree, if we have n nodes, then how many layers do we have? That is a log 2 base n layers do we have. That's so, and each layer we need to read and compare each data once. So for each layer we need to process n data. So in qualitatively, time complexity is n log n. That's what you get. But we can prove this one using mathematical recurrence relation. So here there is a proof. So in merge sort, running time for data n, so we do recursively for each half. So here is a half of the data, and the t of n over 2 is a running time for half of the data. Since we have two halves, it's time 2, and then we need to combine those two results together. So we need to go through each data once. So there is a n step is required, and then each step may have some constant computing time though. So in general, the recurrence relationship is 2 times t of n over 2 plus n is a recurrence relationship. Then t n over 2 is the same as a t n over 4 plus a cn. Then if we eliminate the parenthesis, then we have this one, and then 2 times cn is there. And then t n over 4 is a t n over 8 plus c times n. So, and then eliminate the parenthesis, results that we have this form, 2 times t, 2 times cn. Then here, what we need to figure out is how many 2cn will appear if we keep going down there until you have a t over 1, just one data. So how many steps we are going down? So we can take a look the divider part. So here 4 means 2 to the 2, 8 means 2 to the 3, 16 means 2 to the 4. So compare with the exponent with how many 2cn's we will have. For 2 to the 2, exponent 2, we have 1 2cn. Exponent 3, we have 2 2cn. Exponent 4, we have 3 to 2cn and the like. So if we have exponent k, we will have a k minus 1 2cn what we will have. So suppose n is 2 to the k, then this means 1. So how many steps we will have? Log n steps we are going to have. So the last equation, this part is log n, so that is n. Log n is the resulting recurrence relation for time complexity. So merge sort time complexity is n times log n.